When developing an integrated offshore wind grid, an important question is how to price the wind energy that is generated there. In this presentation, I will go into this topic and make a proposal. My name is Laurens de Vries. I'm an associate professor at Delft University of Technology. I have worked since the late 90s on electricity and energy market design, mainly interested now in long-term questions like market design for all renewable power system, but also capacity remuneration mechanisms, as well as a variety of other topics concerning market design. I'm also the coordinator of the ERA Joint Program on Energy Systems Integration. In this project, my role was to provide an analysis of offshore market design. Before we get into market design, I need to make a little sidestep into why it would be rational to overplant. That is, why it would make sense to install more wind capacity than the grid could evacuate during high wind conditions. The short answer is that this reduces the overall cost of the offshore wind system, but I'll go a little bit into that. Then we're going to look into offshore market design. Our recommendation is to split the offshore grid into different price zones. The price zones are to be defined by which network links are congested, so they're dynamic. This works well with respect to economic efficiency, but may create a price risk for the wind park operators. And so the third part of the presentation is to provide a solution for that issue. First, the issue of overplanting. If you allow just so much wind capacity to be installed as the grid can always evacuate, which actually was the starting assumption of the promotion project, then you never get congestion. However, you also don't use the grid optimally. I would advocate allowing wind park operators to install more capacity. That means that sometimes they cannot run all their turbines, they need to curtail. However, at other moments when there's less wind, they can produce more. And these are the moments precisely when the power price tends to be higher. So I think the wind park operators should be able to decide for themselves how much capacity to install. Thereby, we reduce, as they maximize the value of their grid connection, we also maximize the value of the offshore wind system as a whole, or in other words, reduce the cost to society to the minimum. A tricky thing is, of course, though, that currently wind park operators are being compensated for curtailment, so we don't want to do that much. In the market design that I will present, that is no longer necessary. Here we see an example system that I will use to illustrate different market designs. On the left is country A, which at this moment has a lower price of 23 euros per megawatt hour. And on the right is country B with a higher price. The countries are connected in the north by two wind parks. One has 1,000 megawatts, wind park 2 has 1,200 megawatts installed, and they're both connected with a 1,000 megawatt link to their home countries, and there's a smaller link of 600 megawatts between the two parks. In the south, the countries are also connected via a wind hub. They share a wind hub at sea. The wind hub, wind energy hub, has 4 parks connected. Each park can produce at most 550 megawatts. Right now, we're showing a high wind scenario where each has to be curtailed by 50 megawatts because the total network connection is only 2,000 megawatts. The dotted line shows the border between the countries. In the North Sea, that is the border of the economic exclusive or exclusive economic zone. And so in this case, the price of the wind park 1 would be 23, and it would send all its power to country A, and the rest of the parks, being in the waters of country B, would receive the higher price of 30. Now, wind park 2 would need to be curtailed by 200 megawatts, so it would receive 30 megawatts for the 1,000 megawatts that it could produce. At the hub, the situation is a bit more complex. There also needs to be curtailment there, but it can, even though the hub is in the zone of country B and it receives the price of country B, it cannot send all its power to country B. Half the output has to be sent to country A. This leads to a question, a problem, namely that now we see an export from a high price zone to a low price zone. Question number one is, who's going to pay the difference? Because the wind generators receive a price of 30, but half their power is sold only at a price of 23. Does the grid operator or does someone else need to support this, provide this price difference? Alternatively, if we don't want to flow from the energy hub to country A, we could curtail the energy hub by another 1,000 megawatts, basically cut half its output. Then we would not see this flow from the high price to the low price zone, but we would also not be using our offshore wind system very efficiently. Moreover, we are still not complying with the European rule that says that we should maximize cross-border capacity going from A to B. So the only way to actually have 1,000 megawatts export from A to B would be to curtail the energy hub further, or to curtail, no, that would be the only way, and to basically counter trade. So, and the same problem exists up north, where now there's a zero flow across the border. To maximize cross-border capacity, we would have to curtail Wind Park 2 further to allow more cross-border flows. So this setup leads to problems of either very high counter trades and or unnecessary curtailment. So it doesn't provide incentives for efficient use of the wind park. So to pinpoint the problems, the energy hub receives a high price, but not all its power is actually sold at this price. So who is going to support that price difference? And there's an issue of cross-border capacity that is not maximized in this market design. The only solution would be a lot of counter trading, which would mean a lot of socialization of this cost. The solution that we propose is to divide the offshore wind grid into different price zones that are defined by the existence of congestion. The dotted lines show the lines that are congested in a case with high wind. This is a case for high wind and overplanting. Because up north, more wind, well, actually both up north and down south, more wind energy can be generated than can be evacuated, the wind parks receive a price of zero, or at least the marginal cost of wind generation, which is close to zero. This is a disadvantage of this model, but I'll come back to that later. An advantage is that all links that go from one price zone to another are used to the maximum. So there's full compliance with the European regulation in this regard. There's no need for any kind of counter trading. Another advantage is also that the curtailed energy has a value of zero, so there's no need to compensate park owners for curtailment. However, they do have a lower revenue at moments of high wind. At moments with less wind, the situation is a bit simpler. In this case, all parks receive the price of country A. This is logical, given that the offshore wind grid provides a connection between country A and B, and the price in B is higher. There will always be pressure to move power from A to B, to export from A to B, and to use the wind grid as an interconnector. As long as the offshore wind grid doesn't have very high capacity, this will lead to congestion, and therefore you see a price difference between the offshore wind grid and country B. So all parks now receive the price in A. Their output is lower, so there's no need for curtailment. So we see still that even though the parks get a positive price, they get the lower of the two onshore prices to which they're connected. This would also be the case if overplanting would not be allowed. Then we would have the simpler situation where all power could be evacuated, but the marginal value would be equal to the lowest price of the connected countries. So that would be the offshore price. So price zones, splitting the offshore wind grid into price zones, has some important disadvantages. No need for counter trading and no need to compensate parks financially for curtailment. Another advantage that we haven't talked about is if we have power to X offshore, for instance, power conversion to hydrogen, it also needs this this kind of marginal cost pricing to provide efficient incentives for using the power conversion. The disadvantage is that the park revenues are lower. So how can we fix this? One option is no overplanting. However, then the total average cost of the offshore system will be higher because you're not using your grid optimally. You could also allow overplanting only behind each individual park connection. That would partly relieve the problem, but for instance, it would not provide a solution during the construction phase when maybe 2 out of the 4 parks connected to the wind hub would already be operational, and the 2 others not. And during that phase, the parks should never be curtailed. They could always produce everything, even during high wind. Or if parts of parks were in maintenance, then other parks could produce more. So the most efficient solution is overplanting at the system level. Now you can reduce the financial risks by providing financial transmission rights for the wind parks. This is an established solution, has been in the literature for, I think, about 20 years. Basically, the TSO, the financial transmission rights would give the parks the right to receive part of the congestion rents from the TSOs. However, this conflicts with EU regulations on the use of congestion rents. The solution that we propose is to provide wind parks with put options for onshore prices. The economic outcome is the same as the use of FTRs. However, it avoids the money flow from onshore revenues to generation to congestion rents, and then the need to have to give the congestion rents back to the park operators. Instead, the proposal is to provide the park operators right to onshore prices directly, and so that in the market clearing, at least part of their output is remunerated at onshore prices. Only overplanted capacity or capacity that needs to be curtailed will not receive these put options. Here's a simple example of how this works. One park, 1200 megawatt capacity, high wind. It can only produce 1000 because the connection is only 1000. The offshore zonal price in this simple case would be 0, but you could give the park a put option for the onshore price for 1000 megawatts, not for the full capacity because we cannot evacuate the full capacity, but the put option can be equal to the connection to the onshore, because of course 1000 megawatts is sold at the onshore price. So rather than collecting the full 30 euros per megawatt hour onshore price minus the 0 euros per megawatt hour offshore price as congestion rent, for the capacity of this network link, 1000 megawatts, the put option would give revenues to the park of 30 euros. The remaining 200 megawatt that could produce would be producing at a price of 0, and therefore it should be curtailed. Here's an example of how put options would work in a little bit more complex situation where the wind parks are connected to 2 countries. Basically, the idea is that the available network capacity between the energy hub and country B is allocated to the wind hubs in the form of put options, so to the wind parks. So each wind park would get 250 megawatts of put options for the price in B. Basically, that means every wind park can sell 250 megawatts at the price of B if it wants, because it is an option, of course. Similarly, each park can receive 250 megawatts of options for the price in A, because after all, this is a snapshot, and the price in A may well be higher than the price in B at other times. Now, During the case of high wind, this means that the parks can each get 250 megawatts at the price of B, 250 megawatts at the price of A, and the remainder 50 megawatts would not have a price and would need to be curtailed. For the system as a whole, it would look like this. In a high wind case with overplanting, the hub price is 0, both in the north and in the south. Wind Park 1, which can technically only evacuate to country A during high wind, should therefore only receive options for country A. Therefore, its full output is sold at a price of 23. Wind Park 2 can only receive 1,000 megawatts of options for country B, even though the owner decided to overplant. 200 megawatt needs to be curtailed, but 1,000 megawatts can be sold at the price of B because the park has options for this. And in the south, it is, as I said before, each park sells 250 megawatts at the price of B, 250 megawatts at the price of A, and curtails 50. Now, if there's less wind, the situation becomes simpler. All parks are in a zone with a price of 23. However, they can still use their options to sell in country B. So this improves the revenues of the energy hub because now they can only sell 225, or they can only produce 225 megawatts. And since they each have a 250 megawatt option for country B, they can sell all their output at the higher price of country B, improving their revenues. By the way, this doesn't fully utilize the connection from the hub to country B. So there's also room for 100 megawatts of exports from country A to country B. Up north, Park 2 can sell all its output at the price of country B. And there's also space for some exports from A to B. So to conclude, offshore price zones provide are the best solution in the sense that they provide optimal incentives for dispatch, no need for counter trading, etc. Incentives are also optimal in the presence of storage or hydrogen production offshore. The only disadvantage is that they may offshore price in the case of offshore price zones and overplanting, the revenues may be quite low, at least during certain hours. Put options stabilize these generator revenues. A great advantage is also that in this market design, the wind park operator can choose to what extent he overplants. Overplanting doesn't cut his revenues because he's shielded against low prices during curtailment hours, while he can benefit from the available network capacity to sell more power when wind is less favorable, during lower wind conditions. That's quite important for society because it makes better use of the offshore grid and it provides more power during low wind conditions when there's a need for that power. Thank you very much for your attention, and I look forward to any kind of feedback or questions from you, if you have any.
Part 2. Cross-border hub-to-hub cables. The legal solution. Hybrid asset regulation. My name is Ceciel Nieuwenhout and I work at the University of Groningen in the Netherlands, specifically at the Groningen Center of Energy Law, which performed the legal and regulatory research within promotion. As Laurens already said in the first video, the connection of offshore wind farms is changing. The status quo on the left-hand side shows radial connection and hubs connections. So the radial one is the top one and the hub one is the bottom one on the left side. And what we are going towards is a hub-to-hub or even meshed situation, where you don't have a link only with country A, but also with country B. However, the current legal framework is not yet ready for this kind of connections. What happens if we don't change anything to the current legal framework? there are rules applicable to interconnectors, so to cables from country A to country B, that say 70% of the capacity needs to be available to the markets. But the offshore wind farms connected to the cable would also want to send their electricity to the shore. Efficient dispatch could require trade from the high to the low price zones, as Laurens already explained. Or TSO should make the capacity of this line much higher than what would normally be necessary in order to still comply with the 70% rule and evacuate the wind energy at the same time. Or ultimately, TSOs can decide not to construct the extra link, the one in red, even though there are societal benefits to it. So that would be a missed opportunity if TSOs would not build the red part of the cable, even though it would be a good idea from a societal point of view. So we need to change something. As Laurens mentioned, there's two solutions, the legal solution and the economic solution. So the legal solution will be the topic of this presentation. The problem that we are looking at is actually caused by the qualification interconnection of interconnector, which automatically means that the interconnector rules are applicable to the cable. One possible solution to circumvent this is to introduce a new category in the electricity regulation, hybrid assets. The requirements are a definition, so what is a hybrid asset, and an article in the electricity regulation stating which rules are applicable to hybrid assets. This article should then be adjusted to the characteristics of hybrid assets and offshore grids, because we're now talking about hybrid assets, but the solution should also work for the meshed offshore grid as a whole. The idea of hybrid asset regulation is that you connect at least one offshore electricity production facility, mostly offshore wind, but other sources could also be possible in the future, that connects at least two countries, so country A and country B. And then there's a dual functionality of connecting the renewable energy here and here, and facilitating energy trade at the moments when the wind doesn't blow and the cable capacity is available for trade. Step one is recognition. Following promotion stakeholder consultation, the concept hybrid asset was actually already recognized in the electricity regulation. Recital 66, which is about investments in major new infrastructure, and also about offshore electricity cables, says that offshore hybrid assets with dual functionality should be eligible for some exemptions. And in bold, the regulatory framework should duly consider the specific situation of those assets. However, only an adoption in the recitals of the regulation is not enough. It's also important to adopt it in the operative part of the regulation. The recitals are only there for interpretation purposes, to say what is the context of a certain rule, but without rules in the operative parts, you can't really rely on it. What are the benefits of the hybrid asset regulation solution? First of all, it is compatible with the current economic model that we see, so with the EEZs being the bidding zones. Secondly, it is a relatively simple change. There's low disturbance of the status quo, so national bidding zones are extended in the EEZs, and no changes are needed to the existing interconnector rules. So there's no legal uncertainty for existing interconnectors, and new interconnectors can also be built with the existing rules. And secondly, no changes are needed in the national support schemes, as compared to the other solution that Laurens is going to explain in the other video. However, there are also some challenges. For this solution to work, the EU electricity regulation needs to be changed, and this takes several years. The electricity regulation has just been changed last year, so it would take several years before they would go on for new revision. Secondly, adding an extra category of assets reduces the uniformity of EU energy law. Creating extra categories will make everything more complex. Third, the current market model based on the EEZs remains unchanged. And as Laurens already mentioned, there are several critical problems with the current market model. So if you introduce hybrid assets as a solution, this part will not be solved. This problem will still remain to exist. So that's why promotion also identified an economic solution parallel to the legal solution.